Hello, this is a review of problem 2B.5 parallel disk viscometer. Basically, we're just going to be finding the velocity profile and the theta direction, which is this direction around of the viscometer. So it asks us to postulate small values of, I guess, sigma, or I don't know. What's that symbol? All right, so it says postulate for small values of omega, which is in radians per second, of the velocity profile is form VR equals 0, VZ equals 0, and V theta equals R times F of Z. So the reason the velocities increase as you go out radially is because the thing that's causing the motion is like it rotating around this like pipe in the middle. So when the liquid is in the middle, it only has like a very small amount of distance to rotate. And when it's on the edge, it rotates like this whole circle. So that's why V theta gets larger with R. And postulate further that the pressure is a function of R and Z. In the Z direction, that's pretty simple because you think of just like regular water. When you go deeper in the water, the pressure increases. But for R, it's a little more conceptual, and that's because, let's see, it's basically because of the bubble surface tension on the outside of this viscometer. So usually like this gap is going to be like pretty like small. So it's not going to be like this big, but it's kind of more just for demonstration purposes. But since this gap is so small, there's going to be like a bubble of liquid like bulging over this. And basically like the farther it gets like in towards this middle pipe, the lower the pressure. And as it gets closer to this resistive force, so there's like a force going this way and a force coming this way from like the density of the liquid inside and the viscosity. And so this pressure here is pushing this way and this pressure here is pushing this way, and it's from the accumulation of like liquid through this direction. So as you go this direction, like outwards, the pressure also increases. So the pressure at this lower end is also like higher than the pressure here, and that's because of the normal like in pressure because of like liquid height. So that's where the pressure comes from, the Z and the R direction. Pressure here because of the liquid buildup pushing against the bubble, and the pressure in the Z direction because of just regular fluid mechanics of just the depth of the ocean. At the deepest part of the ocean, the pressure's the highest. That makes pretty normal sense. All right, so from the theta components of the equation of motion, obtain differential equation for f of z. And from up here, we can see that f of z equals v theta divided by r. Solve the equation for f of z and evaluate constants of integration. This leads ultimately to the result of v theta equals this. Could you have guessed the result? All right, so go do that. Yeah, I mean, you can, I'll just put this here in case you want to read that. It's pretty much repeating what I said. All right, so equation of continuity in cylindrical coordinates. All right, equation of continuity in cylindrical coordinates. So you get this, and that's from table B.4-2, equation of continuity. And we're using cylindrical coordinates just because this is a cylinder. Yeah, so cancel this out because it's a steady state. Cancel this out because the problem said there's no velocity in the R direction, and cancel this out because it said there's no velocity in the Z direction. So you're left with this, and the purpose of this equation is basically to just say that dv theta d zero or dv theta d theta is zero. So that's pretty much the whole purpose of that equation. A lot of times your teacher might make you write it, but like when you're doing the work yourself, a lot of times you won't actually have to. Like it's not really like very purposeful besides just proving this, and you can also a lot of times just make that assumption just right off the bat. All right, so now equation of motion for cylindrical coordinates. And we want this in terms of constant density and viscosity, and that's just because it makes the equation simpler to cancel. So if you do it without those assumptions, you'll have to like solve for all these tau shear stresses, and it's kind of just annoying. So since we're thinking in terms of Newtonian fluids, we can just make this assumption that rho and viscosity are constant. So yeah, we're gonna want to use, let's see, what equation did I use? Probably B.6-8. I'm pretty sure because it says rho v or rho g theta, and the direction of the velocity that we're interested in is theta. So that's kind of pretty sure that's the equation I used. Yeah, okay. So yeah, dv theta dt, canceling that out because it's steady state, canceling out VR because there's no velocity in the radial direction, canceling out dv theta d theta because, again, this assumption that we got, or this fact that we got from the equation of continuity. No VZ because that's what the problem said. No VR because that's what the problem said. dp d theta, it's only a function of r and z. We got that from, or we understood that from the last part of the problem. D squared v theta d theta squared, again, same as this assumption here. And dvr d theta, again, no VR, and gravity is not a function of theta because it's usually just a function of z, usually. Sometimes it's not, but in this case, it's obviously gravity is usually in the z direction. So that's why. So yeah, just simplify the equation, and you get this. And I think that's it for part A then. Pretty sure. All right, so from the theta components of the equation of motion, obtain differential equation for f of z, solve the equation for f of c and evaluate the constants of integration. So this result. Okay. So yeah, so just eliminating all these terms, and we get this. And from the previous equation, or from the previous part A, we see that v theta equals r f of z, and so v theta divided by r equals f of z, or v theta divided by r equals f of z. Okay, yeah. So I guess, do I put that in terms of, what do I do? So we can delete this. We can delete this because this just says v theta is a function of z only. So we can delete this part of the equation. So we were just left with mu dv theta dz squared, and then yeah, you can just, the reason I don't divide by r from this equation is just because dz is, there's no, like, it's not dr, so you don't have to hold the r in the equation. So I guess I just get rid of the r from here, and I just multiply it out to the other side. So it doesn't matter. You can just get rid of the r, and that's because one side of the equation equals 0, and it's not a function of r, so you can just get rid of it. Since v theta is not dependent on u, and there's only one term, we can divide out the u. And then, yeah, that's why we can divide out the viscosity as well, because it's not, dz is not a function of, or z is not mu, so you can just divide it out. And it's still true. All right, so integrate twice. df dz equals c1, and f of z equals that. Okay, so now we just do the boundary conditions from there. I guess I just, yeah, I fixed it. Yeah, okay, so I guess I just fixed it when I went over here. But yeah, v theta these two should be flipped here. I don't know why I did that. But yeah, f of b equals theta because v, f of z equals v theta divided by r, and v theta would be the theta times, or v theta will be, or f of z will be v theta divided by r, and v theta is just the radial velocity times, or the sigma value times the radius. So you're just dividing the radius, but hopefully that makes sense. But yeah, these are flipped. So yeah, this is correct here. All right, so applying the law of the wall boundary condition. First boundary condition, which is at z equals 0, f of 0 equals 0, or f of z equals 0. F of z equals 0 equals 0. Yeah, okay, so yeah, so 0, and I'm taking that from this equation. F of z equals 0, add z equals 0 plus c2, so c2 equals 0. And then the second boundary condition, plug that in, phi equals c1b minus 0 again, because that's we solve c2 equals 0. And then we solve for c1, which is phi over b, and vz equals, or sigma over b. Vz equals sigma over b times z, and then we convert vz to v theta with this equation here. So f of z equals v theta divided by r, and yeah, we just convert basically and solve for v theta equals phi r times z over b. And yes, it kind of makes sense because just like look at this profile here. The velocity is increasing as you go out and decreasing as you go down. So I mean, that kind of just makes sense. It's increasing as you go out, and as z gets closer to b, it goes up. So as you go higher, the velocity increases as you go higher, and it increases as you go out. So that kind of makes sense. Linear. Well, it's not linear because there's two variables, but yeah, it kind of makes sense. All right, so part C. Show the desired working equation for deducing the viscosity is that. Okay, so looking at the blurb below 3.6-54 for info, guess we'll go there. Next we have evaluate the torque needed to maintain rotation of the sphere. This will be the integral over the sphere surface of the tangential force. This exerted on the fluid vessel. Okay. So we gotta find the tangential force of the over the sphere, which is going to be, what is it, tau z theta, and that's because why is that? Because f is a function of z and the velocity direction is theta. Okay, sure, that makes sense. So yeah, you got to multiply it by the moment arm, and the moment arm of a simple circle is just the radius. And so you got to take that integral with respect to dA, and dA is the differential area of a circle, and dA is just basically just like this area here, where this radius is r plus delta r, and this radius is just r. So you got to subtract those two from each other. So it's pi times r plus delta r squared minus r squared, and that's obviously radius, or area of a circle is pi r squared, and you're just subtracting this whole, or you're taking this whole big circle, including this empty space in the middle, and then you're subtracting that empty space. So that's kind of just like the way to calculate the area of a ring. So yeah, the the radiuses, the r squares cancel out, and this delta r squared cancels out because when you're doing an integral, the dr is basically an infinitely small value that you're integrating over. So if you have this infinitely small value, the square of an already infinitely small value is going to be like infinitely small. So like say your infinitely small value is like 10 to the negative 9. If you square that, you're going to get 10 to the negative 18. And that's like way smaller than 10 to the negative 9. So you can just cancel that out. Hopefully that makes sense. All right, so from table B.1-12. Oh yeah, is there okay, yeah, no. Okay, from table B.1-12, you can get the definition for this. Tau. So you get that. This one's going to cancel out because there's no v in the z direction. There's no velocity in the z direction. So tau theta z equals negative mu dv theta dz, and now we can find tau z in defined terms by most from the previous found theta velocity. So you're just plugging in this equation into here, and then we're gonna integrate and find like the actual definition. Okay, so yeah, just check the derivative of this with respect to z. Obviously there's one z in here, so you just take the derivative of the z, which is just going to be 1. So that makes sense. So we have all the components required to solve for the torque. Tz equals this, basically. Bounds are from 0 to r, as those are the bounds of the radius of a circle. And so now we're just going to do the integral. What is that? Not exactly sure why this is positive. A negative force is basically just the same as a positive force, besides it's just in the other direction. I'm not sure why. Yeah, remove all unnecessary terms from the integral completely. So this, since it's a dr integral, any terms that we can just take out from, like divide out of the integral and multiply it to the outside, do that because it just makes integration easier to look at. So that's all of these terms that basically just aren't are. So yeah, do the integration, and tau z equals this, and now we're just going to solve for the viscosity. And this is the same answer as given. So yeah, advantages and disadvantages. Disadvantages. One advantage is that it's a single mechanism, and another advantage is that tau z is likely easier to calculate with formula that relates required voltage to keep theta constant with tau z, which usually is probably going to be an amperage, but everything's an amperage. But it's probably an amperage. But yeah, it's probably a pretty simple mechanism. Some disadvantages is if you want to like it's probably pretty hard to clean that thing out, to be honest. Like if you put a viscous liquid in there, it's like, how are you going to get it out of that little crevice there? Like if you can't get it out, it's probably going to mess up readings of other liquids. And also the liquid must be viscous enough so the fluid can be held in place. So obviously if the surface tension isn't like strong enough, it's just going to spill out of there. So that's also another thing you need to think about. Yeah, and again, I say it's hard to clean. All right. So yeah, any questions about this problem, please comment. Any questions about other problems or problems you want me to solve, please comment on that. I've done some problems outside of the first 3 chapters of each book, but mostly the chapters within the first 3 chapters of each section are what I kind of specialize in. So yeah, please subscribe, and bye-bye.